So let's continue on DC mode. Last lecture, we discussed about this example. Basically, in DC circuits, every inductor will be replaced by short circuit and every capacitor will be replaced by an open circuit. Then the only elements that we will have circuit elements are three: resistors, voltage sources, current sources. Then we mentioned also about how to find the equivalent resistance. So for example, how to find the equivalent resistance of this circuit. So it will be replaced by only R equivalents, and we have only voltage source and R equivalents. So how can we find R equivalents? I think you are familiar of this in physics, to do something called series and parallel. Now we will go more details in series and parallel, but we will discuss this in our own way. So it's the same concept that you know before, but now we are trying to make some standardized analysis in how to know if these two elements are really in series or if these two elements are in parallel. So basically, series resistors. So how can we know these elements are in series? Basically, there need to be two conditions, or these two conditions must be satisfied. So the first condition, sharing the same currents. We can say these two elements are in series if and only if they are sharing the same currents. We have another condition which is common in one node. Common in one node, then we will say these two elements are in series. But basically, I would suggestly recommend to consider sharing the same currents. If you find these two elements are sharing the same current, then we will say those are in series. So basically, let's look at this circuits. So we will see R1 and R2 are sharing this node. I will say this is the yellow node. While R2 and the other resistor, there is another node. So as a result, since R1 and R2 are sharing the same node, and the other thing which is these two are sharing the same currents, because imagine there is a current from A to B. This remains IAB. It will not be changed. So as a result, we will say R1, R2, up to Rn, all of them are in series. Then in series, we will, the formula, the equivalent will be there, sum R1 plus R2, etc. plus Rn. Okay? Let's imagine this scenario, another scenario. Here is point A. Here is point B. This is 7 ohms. This is 1 ohm. So by looking at 1 ohms and 7 ohms, are those in series or in parallel? Of course, in series. Why? The first observation, you can label the nodes. So the 7 ohms and 1 ohms are common in one node, which is the orange node. And the other thing, try or imagine there is a current from A to B. Then will this current be splitted? No, therefore they are in series. So we will say their equivalents 8 ohms, which is 7 plus 1, 8 ohms. This is RAB. Okay? Another scenario. Here is 1 ohms, 7 ohms, 2 ohms. Here is A, here is B. Now I need to find the resistance between A to B, the equivalent resistance. So the 1 ohms and 2 ohms, are those in series or in parallel? Or are those really in series? Let's not forget, let's not talk about the parallel, let's talk about series. Are those in series? 1 ohms and 2 ohms. Let's try to label the nodes. This is node pink, this is orange, this is purple. So look at 1 ohms and 2 ohms. They are common in the purple node, right? So does this mean those in series?
Current splits.
Because the current splits. So this is not in series. These two are not in series. So here in this situation, even though common in one node, but not sharing the same currents. So therefore, those are not in series. Okay? So it's very important to notice that even though they are common in one node, but they are not in series, so the point is, when you do an inspection, make sure they are sharing the same currents. Imagine there's a current flowing from point A to point B. Will this current be splitted or not? Now, how about parallel? Parallel definition means 2 conditions, which is common in 2 nodes, or actually in addition to this, sharing the same voltage. Series sharing the same currents, parallel sharing the same voltage. And in order to check if these elements are series or parallel, I encourage you to look for if they are common in 2 nodes. Okay? Look at this circuit here. So let's label the nodes. This is node A, all of it node A, because there is no elements connected between these points. No elements, they are all sharing one node. Then the other node, which is node B. So we have 2 nodes. So R1 and R2 are common. R1 between node 1 and 2, or A and B, R2 between A and B, up to Rn between A and B. Since they are all common in 2 nodes, therefore they are sharing, or they are in parallel. So here, VAB actually equals V1, VR1 equals VR2 equals to VRN, because they are in parallel. So we will say, in order to find R equivalent, 1 over RAB equals 1 over R1 plus 1 over R2, etc., plus 1 over Rn. So what matters, what will tell me that these 2 elements are in series or parallel, or this parallel actually, how will I know these are in parallel? Basically, you need to determine if they are sharing common in 2 nodes. Now, I'm gonna write this example. Here is, we have R1, here is, we have R2, and here this is AB. Now, are those in series or in parallel? The best thing to determine this is to label the nodes. This is a node, and this is a node. So we will say R1 between the yellow and purple, R2 between yellow and purple. Therefore, they are sharing 2 nodes, right? Common in 2 nodes. Since they are common in 2 nodes, this means they are in parallel, right? So as a result, we will say 1 over RAB equals 1 over R1 plus 1 over R2. Sometimes, as a shortcut, we can say RAB equals R1 parallel with R2. Something like that. So if we use parallel, simple here, this means these 2 elements is parallel. And there is a special rule for 2 parallel resistors. Special formula only for only 2 parallel resistors. 2 parallel resistors, which is RAB equals their multiplication over their sum, R1, R2 over R1 plus R2. This is valid if and only if we have 2 parallel resistors. Otherwise, it will not be valid. Only 2 parallel resistors. two parallel resistors. Okay? So we don't need to say 1 over R1 plus 1 over R2. While we consider multiplication over the sum, we can use this as a shortcut and to do with this in fast way. However, the formula 1 over R, this is the general formula that's valid everywhere, every time. Now there is another definition called conductance. What does conductance mean? Basically, we know Ohm's law, V equal I times R. Then most likely the voltage is well known. So we will say like, what's the wall outlet? 120 volts. What's the battery voltage? 12 volts or 9 volts, whatever. So we know the voltage, but we don't know the current. So most likely in our analysis, we need to calculate the currents. So in order to calculate the current, we will say I equal V over R. That's according to Ohm's law. Sometimes, most likely when we build a software, especially on large networks, we will write it as a matrix. So, or I as a vector, the resistance as a matrix, so it will be R inverse times V. That's how we do most likely the calculation when we do deal with very large systems. This is in all, very big systems to make some analysis in current calculation. For example, for open university electrical connection systems, we need to do some studies. Again, the voltage is known. We know what's the voltage. While R is related to the load. So we can know like the load, we have these classrooms, we have these machines, this is for the AC unit, so we can predict what's the load. But the thing that we need to do is to calculate the currents. So we will use like I equal R inverse times V. Again, we're using inverse because we are dealing with matrices. Then, in order to deal with these matrices, most likely we will use software to do it. So we can use like software like MATLAB, or we can use any other softwares like C language, whatever, to do these softwares. Like sometimes in our analysis we can use for loop, and we can do some iterative techniques, something that's called numerical analysis. I'm not sure if you are familiar with this, or maybe you will learn this later in math, which is called numerical analysis. Then we used to do several analyses. Then in this kind of analysis, we will have for loop or while loop, something like that. So we will do this expression, for example, 1,000 times, like I equal to R inverse times V. So the thing is, it's a multiplication that can be fine. But what's the problem that we have is doing the R inverse. The inverse actually consuming a lot of time, especially in a lot of computational calculations in the computer, which when we do it 1,000 times, this will make the program slow, so slow. So what should I do to deal with this? We will say that R is actually fixed, it's constant. So why don't we calculate it once, and that's it. Why don't we calculate R inverse outside of the loop? So we will say like G equals to R inverse. Then we will make for loop such that I equals to G times V. Why don't we do this? So in this kind of things, we will avoid calculating R inverse 1,000 times. So let's assume that calculating R inverse takes 1 second, then we can save 1,000 seconds in our program. And how for big or for large systems, we can save sometimes hours because of this. So when we do this analysis by calculating R inverse once and just multiply I equal G times V, then the product is actually easy on the computer, in the software. It will take shorter time. But again, the inverse take a lot. So as a result, we assumed a parameter is called G, intermediate parameter is called G equals to R inverse, or in other words, G equal 1 over R. And we found a physical meaning for that, which is called conductance. R, resistance, which is for limitation of the current, while conductance, which is how much the current capability to transfer. So conductance is 1 over R, and the unit of it is Ohm inverse, or in other words, we call it Siemens. That's S. So most likely we are using the conductance in programming, but in circuit analysis we will not use it a lot. Actually, I don't think in this course we will use the conductance. We will use only resistance. But I'm gonna say like conductance has important applications because we will use this a lot in the programming. And again, it's the same thing, 1 over R. That's it, nothing changed. So whenever you see the simple G or the conductance, it's just 1 over R, 1 over the resistance. So again, we will not use this a lot, but this has been used in the programming, and here I showed you why we need this in the programming. Okay? Any question? Okay, so you will see later here, like series inductors, parallel inductors. I'm not willing to cover this. Actually, I forget to delete these slides because last semester I deleted them, but this semester I forgot. So series parallel inductors, series parallel capacitors are not included. The only thing that you need to have series and parallel resistance. Now there is network example. Before discussing the network, let's go to the worksheets number 1. So let's refer to worksheet number 1. Go here to Canvas. Files. Worksheets. So we have around 15 worksheets. Let's go to worksheet number 1. So this worksheet about the equivalence resistance, forget about inductance capacitance. So here it will tell you the procedure and how to find our equivalence in more organized way. So the first step, you need to identify all of the nodes in this circuit. How to identify the nodes? You can label them as node 1, 2, 3, 4, or you can label them A, B, C, D, etc. Or you can use the colors, orange, red nodes, purple, whatever. Then you need to keep in mind that these two elements are in series if they are sharing in one node, and I will write here also sharing the same currents. Sharing the same currents. Then we know these in series. In parallel, if they are sharing both nodes, while short circuits, if it is the same node in either sides, then we will say these two elements are short circuits. Okay, then what should I do? After you start identifying the nodes, you need to start from the furthest point away, the furthest point from the observation. Then start doing some simplification. If these two are in series, if these two are in parallel, then if, for example, you try to do analysis and you cannot judge, these two are not in series, these two are not in parallel. Okay, what should I do? Look for another part of resistance. So don't fix or remain here. Maybe it's too early to do this simplification. Let's do the others. Then, after making every combination, please make sure to redraw your circuits with the updated one. So this is something very important. Then you can combine them step by step. I'm going to write here a small example, like brief example, like here. This is 1 ohm resistor. Here is point A. Here is 12 ohms resistor. 6 ohms actually. 6 ohms resistor. 3 ohms. And we need to calculate the equivalence. So the first thing that's I encourage you is to label the nodes. This is a node. This is a node. This is a node. Okay? Then, if someone say, let's make the observation between the 12 ohms, look at the 12 ohms and the 1 ohms. Are those in series or in parallel? Actually, they are not in series, are not in parallel. They are not sharing the same node. They are not common in two nodes. So what should I do? Again, I said, whenever you see something that they are not in series, not in parallel, then don't do this. Look for other resistors. So we will not do it. Recall, start from the furthest point away from the observation. Here's my observation points. What's the first resistor? Which is this 3 ohms. Now look at the neighbors. 3 and 6. Is there any relationship? Yes, they are common in two nodes, therefore they are in parallel. Then how about 12? Yes, they are in parallel. So we will say that 3 parallel with 6 parallel with 12. So I'm going to say 1 over their equivalent, I'm going to call it as R1 equal 1 over 3 plus 1 over 6 plus 1 over 12, which will be 7 over 12. Therefore, R1, don't forget to flip them, which will be 12 over 7 ohms. That's one of the common mistakes. Many students forget to flip the answer. Now, after doing this simplification, redraw the circuits. 1 ohms resistor remains the same. Then the equivalent, this is R1, which is 12 over 7. Then this is A, this is B. Let's relabel the nodes. Here is the green node. This is the purple node. Then this is the yellow node. Now, what's the relationship between R1 and the 1 ohms resistor? Series. Why? Because sharing the same current. Imagine there is a current flowing from point A to point B. It will not be splitted. Therefore, they are sharing the same current. Or you can say as well, they are common in the purple node. And the current will not be splitted. So we will say that RAB equals to 1 ohms plus R1, which is going to be 1 over 12 over 7. Then the answer will be 19 over 7 ohms. This is RAB. Okay? Keep in mind, after every simplification, you need to redraw the circuit. So this is RAB, here is A, here is B, then that's the answer. Any question?
Seven come from?
Which one? The
7 over 12.
Yes, because here 1 over 3 plus 1 over 6 plus 1 over 12 equals 7 over 12. Then flip it, 12 over 7. Okay, now let's go back again to worksheet number 1. There is an example. Here is the example. You need to solve the equivalent resistance for RAB. So this circuit is actually not easy. How can I find the equivalent resistance? So, I mean, maybe the previous one in this example, using what you learned from physics, you can find it without the need to use our own procedure. But here, it can be kind of difficult. So how can I define the equivalent resistance? There is observation point at AB. According to our procedure, please label the nodes. So the first step is to label the nodes. Here are the nodes after being labeled. These nodes, or the answer already exists in the worksheet, so we didn't write anything. Then by making some observations, you will see that the 4 kilo ohms between the orange node and the orange node, which means the same node at both ends. Same node at both ends, this is the definition of short circuits. Short circuit, which is the same node. You are connecting both sides at the same node. It looks like when you go to the wall plug and try to connect the positive with the negative. Short circuit. So the same node at both ends. Then, with this short circuit, this means this element is short circuit, so basically you need to erase this resistor like it does not exist. Erase it. Just use the eraser and erase it. The next simplification, look at some points that are away from my observation. So let's look at the 2 kilo ohms here and 2 kilo ohms here. Is there any relationship between them? Do you think, can this be in series or parallel? series. How? Imagine there is a current flowing, then there will be the same current, right? How about the corner, the bottom corner here? 2 kilo and 2 kilo. These two are in series as well, right? Now, can I make the 4 kilo ohms and with other 2 kilo ohms here? No. So, don't do too much simplification. I mean, too much procedure. So, like, this is enough. Now, I'm ready to redraw the circuit. So, 2 kilo ohms plus 2 kilo ohms equal to 4. 2 kilo ohms, 2 kilo ohms equal to 4. So, that's the equivalent circuit. Redraw the circuit and relabel the nodes. So, this is the 4 kilo ohms, 4 kilo ohms. The short circuit, which means we have erased the 4 kilo ohms because short circuit. So, this is the new circuits. Then relabel the nodes. Yes?
Can you go over again, how do we know that was a short circuit?
Okay, look at the 4 kilo ohms. It's an orange node at both ends. If it is the same node at both ends for any element, this means it is short circuit. And then you will erase it. Okay, now with this circuit, someone can say 4 kilo and 4 kilo, 4 kilo, all of these three are in parallel. That's what it looks like, right? I do think so. Label the nodes. Look at 4 kilo ohms in the top and 4 kilo ohms in the middle, between orange and green. Then these two are in parallel, right? Yes. How about the bottom here? 4 kilo ohms at the bottom, between green and blue, not green and orange. So they are not in parallel with the bottom. So as a result, we will only say the top and the middle are in parallel. Okay? So 4 kilo parallel with 4 kilo means 4 kilo times 4 kilo over 4 kilo plus 4 kilo. In other words, will be 4 kilo over 2, so the answer will be 2 kilo ohms. So their equivalent will be 2 kilo ohms. Then the next step, redraw the circuits. No other simplifications that I can do. Then redraw the circuits. Redraw the circuit and label the nodes. So this is the circuit, their equivalent now it's 2 kilo ohms. Now, 2 kilo ohms and 4 kilo ohms, are those parallel or series? Again, it looks like parallel, but actually they are not. Okay, are those in series? How? Imagine there is a current from this point to this point. Will this current be splitted? No. So those show you the same current. While they are not in parallel because this is orange, this is blue, then they are not in parallel. So as a result, 2 kilo ohms and 4 kilo ohms are in series. So their answer, 2 kilo plus 4 kilo equals 6 kilo ohms. So they will be look like this. Now, does the 6 kilo ohms and 2 kilo ohms, are those two in series or in parallel? They are common in the blue node, right? So are those series? Imagine there is a current flowing. Are those sharing the same currents? No, they will not. How? If there is a current flowing, it will be splitted here and here. Then they are not sharing the same current. So here is a tricky thing. Or imagine there is a current flowing here, it will split here and here. So they are not sharing the same currents. The other thing, which is 6 kilo ohms between the blue and orange, 2 kilo ohms between the blue and the orange. Then they are in parallel because common in two nodes. So we will say 6 kilo ohms parallel with 2 kilo ohms, which means 6k times 2k over 6k plus 2k. So 6 times 2, 12 over 8. So the answer, I think, will be 1.5. Then redraw the circuit, 1.5, then that's it. Okay? So again, when you do your analysis and finding equivalent resistance, please keep in mind you need to simplify step by step, okay? Any question about finding our equivalent? Okay, now, so please make sure to practice more examples. I think I'm gonna mention some recommended problems. Let me see if I mentioned them. Where did I write them here? Okay, maybe not now. I can, maybe in Friday lecture, I can give you the recommended problems. Let's go back to the notes. Now we need to solve DC circuit analysis. How to solve the DC circuits? This question says determine all of the electrical quantities. So I already wrote the procedure in, I think, two lectures ago. How to do the procedure, which is first thing, identify all of the voltage or label all of the currents, directions, voltage polarities, right? So you need to assume all of them. Then let's look at the circuit. So it says determine all of the electrical quantities in this circuit. And we mean by electrical quantities, voltages and currents. So we need to determine all of them. And remember, we are in DC, so all of them must be upper cases. So how to solve this circuit? So let's label all of the currents. The current should go out from the source according to our procedure. The current must be out from the source. While for the resistor, we want the currents to enter the positive polarity of the resistor to make sure Ohm's law is positive, right? So let's assume the current directions. The current will start from the source. So here is I source. Now, for the 4 ohms resistors, I source remains, right? Then at point B, it will be splitted. So I'm going to call this one as I1, this one as I2. Then for the 8 ohms, remains I2, no change, right? Now all of the currents directions has been labeled. The next thing is to label the voltage polarities. So the voltage polarities for the V source, it's already been given. For the 4 ohms resistor, keep in mind we need to make Ohm's law positive, so the current enters the positive polarity of the voltage. So it will be plus minus. I'm going to call this one as V1. Here, plus minus V2, plus minus V3, plus minus V4. Okay? Now, all of the current directions are given, all of the voltage polarities has been assigned, all of them. Current directions and voltage polarities are or have been assigned. Then, my question is, what should I do next? According to our procedure, start from the extra given information. Do we have an extra given information here? No. Okay. Then, following the procedure, do KVL, KCL, Ohm's law, such that there is only one unknown. Okay, how can I do it? We don't know anything. We don't know any of the voltages, any of the currents. The only thing that we have is the voltage source. We don't know the current source. So is there any way to modify this circuit so I can have only one unknown? So look at the source, because the only given thing that we have is the source, right? 100 volts, 100 volts. So we know voltage source. We don't know current source. So how can I know I, the source current, IS? How can I know the current of the source, which is IS?
Ohm's law with the first resistor.
Ohm's law, equivalent resistance. Great idea. That's it. So basically, if we modify this circuit to be, looks like 100 volts, R equivalents, and here is I source. So actually, if we can find R equivalents, then the only unknown is I source, right? So we will say that I source equals to V source over R equivalents. So we need to know R equivalent first. Then if we know R equivalent, we can know I source. Then we can do the circuit. Then the problem will be solved. Case closed. Okay. Now, how to find R equivalents? Basically, keep in mind we need to find R equivalent with respect to the source. So we need to calculate R equivalents. Basically, I can write this here. Here is 4 ohms, 10 ohms, 7 ohms, 8 ohms, and my target is to calculate R equivalents at the source, like this. I just remove the source and I need to calculate R equivalents. So how to find R equivalents? So basically we need to label the nodes, then do series and parallel. Now since we have a quiz, I'm gonna end up here today, but try to do this at home to find R equivalents. The R equivalent must be 10 ohms. So the answer must be 10 ohms. You can try it at home. The next lecture we will continue in this example.